Hi everyone, my name is Zhe Hu, and thanks for your interest in our work. VIVA, a benchmark for vision-grounded decision-making with human values. This is a joint work with collaborators from Hong Kong PolyU and CASE. And I'll start with background and motivations. Recent large vision language models have demonstrated remarkable intelligence across diverse tasks. With their more and more integration into our daily life and their potential applications for embodied AI, we want to ask, can they understand human values and make proper decisions to handle human-centered situations? And here are two examples. In the first one, witnessing an old people falling on the ground, human beings can make decisions to assess the situation and provide help by calling emergency services for professional medical assistance. And such decision-making process aligns with underlying human values of showing compassion and respecting expertise. Similarly, in the second example, seeing a person struggling in the water, people can make decisions to help the person by looking for a throwable flotation device and throw it to the person to help them stay afloat. And similarly, such decision-making process also aligns with underlying human values, including duty to help and promotion of personal safety. Although this task is quite obvious and easy for human beings, they remain challenging for VLMs. Such decision-making requires multiple abilities, including perception of the situation, reasoning and comprehension of the situation, and finally give the proper action. Meanwhile, to make the action trustworthy and reliable, the underlying human values should be incorporated as fundamental principles to guide the process. With our motivations, in this study, we propose VIVA benchmark, which is a pioneering benchmark aimed at evaluating the vision-grounded decision-making capabilities of VLMs with human values for real-world scenarios. Specifically, VIVA contains 1,240 images depicting diverse real-world situations as shown in this bar chart. Each image includes annotations of an action to handle the situation, relevant human values influencing decision-making, and accompanying rationales. We hire 6 in-house annotators to participate in the annotation process. Based on our annotations, we design tasks to assess the model decision-making abilities at different levels. The first task is level 1 task on action selection. Given an image representing the situation, along with a question and 5 options for potential actions, the model is tasked with selecting the most suitable option. So for example, given an image where a bunch of person is walking on the thin ice, which is dangerous, we ask the model to select the most suitable action to handle the situation, and the answer here is C, shout to warn the individuals about the thin ice from a safe distance. We formulate this task as a multi-choice question answering. We further propose level 2 tasks on value and reason inference. We require the models to base their decisions on accurate human values and provide appropriate reasoning to justify the action selection in level 1. So basically, we not only want to measure whether a model can make the correct decision, but also want to know whether they make the decision based on the right answer, based on the right reason. So specifically, given the situation, question, and the model selected answer, for value inference, we ask the model to classify whether such decision making is relevant to the value. For example, it is relevant to the duty of care, but it is irrelevant to promotion of recreation. For reason generation, we ask the model to write a short passage to explain why they select such action. For evaluation metrics, because level 1 task of action selection and level 2 value inference are classification tasks, we use accuracy as the evaluation metric. For level 2 reason generation, because it's a reference-based text generation, we first use semantic score where we calculate the average of BERT score and blue rate. We also propose a ChatGPT-based score where we use ChatGPT to evaluate the model outputs and give a score from 1 to 5. Notably, a model is assessed only on level 2 samples for which the corresponding level 1 answers are correct. Besides the individual evaluation metrics, we further propose the combination scores to evaluate the overall performance of both level 1 and level 2 tasks. The first one is action value score. For this one, we evaluate the overall performance for action selection and value inference. We calculate the score of use the product of the individual accuracies for action and value. The second one is action and reason score, where we evaluate the overall performance of action selection and reason generation. So specifically, we consider correctly predicted labels of action selection that has a GPT score of the generated reason equal to or greater than n as correct. Here, n is the threshold, and in our experiments, we set n as 4, 3, and 4. And here it's our main results. We include both commercial models as well as open source models. Notably here, we provide GPT-4 Turbo model only for reference because this model is also used in our data annotation process. From the table, we can see commercial models typically yield better results than open source models. However, even the SOTA models, GPT-4 Vision, still faces challenges on this task, where it only achieves 7488 scores on accuracy of action selection and value inference. This indicates that there's still a long way to go for this task. We also conduct analysis to see what features might be useful to improve the model performance. Our first conclusion is that predicting consequences in advance can improve model action selection. So specifically, given the situation and several action candidates, we first ask the model to predict the potential consequence of each action and then incorporate the predicted consequence into action selection to see whether it can help the model to improve their performance. Specifically, we incorporate consequences predicted by different models, including GPT-4V. Self means the model itself, and also we propose a llama predictor. From this table, we can see GPT-4 predicted consequences can bring improvements for our models. However, smaller models often cannot accurately predict consequences. Meanwhile, our fine-tuned llama model, which has 8 billion parameters, is also useful to bring the performance gain. In our second analysis, we show that incorporation of relevant values can enhance action selection. So similarly, given the situation, we first ask the model to predict the relevant values and then incorporate the values into action selection to see whether it can improve the model performance. We include values from different models, including GPT-4 and also the model self-generated value. And we also incorporate the Oracle value. From this figure, we can see that incorporating both Oracle and GPT-generated value is useful to improve the model performance. However, incorporating the values generated by the smaller models cannot bring a performance gain. This indicates that open source VLMs still face challenges associating situations with relevant human values. We also provide error analysis, and here are 4 common errors made by the model. The first one is incorrect recognition of the situation, where the model fails to incorrectly locate or recognize the visual features so that it makes the errors for action selection. And the second one is action selection with incorrect values. The third one is misprioritized response to an urgent need. And the first one is unprofessional assistance. I recommend you to read our papers for more detailed discussions of this part. So in conclusion, in this work, we provide a pilot study on the task of vision grounded decision-making with human values, and we propose a multimodal benchmark, VIVA, which covers a wide range of situations with annotations of actions underlying human values and reasons. We further conduct extensive experiments about VLM performance for our task and also provide thorough analysis. Thank you again for the listening, and you can find our data and code on this GitHub repo.